Hello and welcome. Hello, Saverio. We said we would start
Hello.
15 minutes past 5 local time. So you will start in 5 minutes if that's all right with you.
Okay, perfect. Yes, I'm here just waiting for you. So in 5 minutes, I will start.
Yeah, if you want, you can already share your screen.
Absolutely. Wait a minute, I can share also camera. Hello from Bern to everybody. And now I just stop the video and try to share the screen. Does it work?
It works perfectly.
Okay, so I'm here. Just tell me when I should start.
Yeah, just a few minutes. Let's give people finish their teas and we will start.
Okay, because it's a tea break. Okay, excellent.
So welcome back to, let's say, the evening or late afternoon session. So we have one talk by Saverio Braccini from University of Bern and from Albert Einstein Center. It's very cool. I need to pronounce it for fundamental physics. So Saverio will talk about production of new radioisotopes. So Saverio, floor is yours. You can start.
Okay, thank you very much. Thank you very much for the kind invitation. And my apologies not to be with you in person in Turkey. Unfortunately, I have exams in these days and was unable to participate, but I'm glad anyway to be with you. And don't hesitate to put questions at the end and also to contact me afterwards. In particular, my colleague Gehan Hunel has my email, which is easy, saverio.braccini@lhep.unibe.ch. Okay, so I will talk for about 25 minutes, as we said. Correct, 25 minutes is correct. About the production of new radioisotopes for theranostics using a medical cyclone. In particular, I will report about our studies and developments here at the medical cyclone that we have in Bern. Can you hear me well? No feedback. Can you hear me well?
Hear you well, Saverio, and you have the floor, so 25 or 35 as you like. So we have the time. So
yes, hear you well.
very well.
All
so
right. Okay. So as you can see here in this title, there are some keywords: radioisotopes, theranostics, and cyclotron. I will try to go through them. And in particular, I would like to go through what medical PET cyclotrons are. Typically are tools for medicine used in hospitals, but they have a very high scientific potential. And I will report about it. I will tell something about our project that was born actually with these two goals: production for the hospitals and research, multidisciplinary research with the same facility, same structure. I will quickly pass through the positron emission tomography and the isotopes that we usually conventionally or daily, and these are typically produced with liquids, bombarding liquids. I will put the laser here. So, but if we bombard solids as we are doing here, we can do much more. In particular, these new radioisotopes for theranostics that I will tell you what it is. Of course, this you need a translation of tools and methods from high energy physics into what basically we are doing here. What are medical cyclones? There are several kinds, in particular the big ones like this one that we have at PSI for proton therapy, the category IA. About 70 MeV, maybe you heard about. There is one in Nantes in France, one in Italy, north of Italy. But what you typically find in hospitals are those, this in red, the category D, which feature 1525 MeV and currents of around 100 microamps. These are the medical cyclones that I'm concentrating about. There are those, they are quite small, about 1 meter. This is 1 meter. They are typically 2 meters diameter. They are small machine, compact machine, and they feature, as I said, 20 MeV protons around. For instance, that is this one, has 18 and 100 microamps. They are designed for hospitals, and there are several in operation. In Turkey, you have at least 10, I would say even 20, mostly in industries. Why these numbers? Because physics has to answer medicine. So the question comes from medicine. Basically, what the medical doctor wants, they want dose of radio traces, typically a sugar marked with F18, and one dose is about 400 megabecquerels. And you have to be able to treat maybe 10 patients in a row. This means that you have to produce gigabecquerel of fluorine-18, and the cross-section, as you can see here, this is physics, is peaked at about 6 MeV. So this justifies the fact that you need energy in the order of 20 MeV. And the current, if you make the calculations based on the cross sections, it turns out that you do 500 gigabecquerel with 150 microns. So basically, these machines are designed to fulfill a medical demand. The half-life of fluorine is 110 minutes. This means that the production have to run every night because the patient comes in the morning. What can you do in the morning? And during the day and in the weekends, you can do research. Just for having an idea, a beam is typically 1 centimeter wide, and you bombard like 3 centimeter cubed or 3 grams of water to do this job. PET, you probably already know, is like a relay race. You have physics, then you have radiopharmacy, then you have medical physics, and examinations and diagnostics at the end. This is like a relay race. Everything has to run coherently and perfectly every night. This is the routine. But of course, as we said, there is much research on new radioisotope behind this. What we have in Bern, we have a laboratory with a cyclone like this that is daily used by our daughter company, Swan Isotopen AG, for daily production of FDG, fluorine sugar, let's say. And we have a beam line. This is our point of strength. We have a beam line and a laboratory here, a bunker, basically. This is used by my group and allows all the research that I'm talking about now. Together with the physics laboratory, where we have gamma spectroscopy, alpha spectroscopy, and all the detector developments we are doing. Important to remark that we are able to produce beam currents down to picoamps. So we can do currents which are completely out of the scope of these machines, much down to perform, for instance, cross-section measurements. This is a sketch of what actually doesn't concern physics, concerns radiopharmacy and chemistry. This is up floor for us, up with respect to the cyclotron. We have 3 production labs by the company and 1 research lab by the Inselspital, the Clinic of Nuclear Medicine. You can see here, basically, they take the products that we do with the cyclotron and then they build the molecules that will be injected into the patients. But this is basically something else. It's not basically our task as physicists. Let's go back to physics. This is the cyclotron opened, and you can see here the beam line. Here you see the Ds, is very beautiful. And what we have, as I said, as a particularity is the beam line. The beam that gets out of the cyclotron in a typical output, one of the 8, is 1 centimeter diameter, you can see here. But with the beam line, you can make a beam which has different intensity and different size, down to millimeters. And this allows all our research activities with the beam line. I put here the reference to our papers that you can have and give a look to it if you want to know more. What is theranostics? Important. Theranostics is a new modality in nuclear medicine that looks towards personalized nuclear medicine. Basically, the idea is to have a molecule, a biomolecule, not a sugar, typically a protein or a peptide or an antibody, and label it with an agent or an isotope, which is beta plus or gamma emitter for PET or SPECT. And at the same time, another labeling you can do with alpha, beta, or Auger emitter for therapy. As you can see here, radiation goes through the DNA and kill the cells. In this way, you can have control of what you are doing, where the agent goes, because you have the imaging, and you can also follow your therapy in time. Promising pairs of these isotopes, one for therapy and one for diagnostics, are listed here. All what is involved are isotopes in which we are, as group of them, involved directly. The problem is that if you want to bombard these substances and produce these isotopes, you need to bombard powders, which are typically enriched in the isotopic fraction and are very expensive. So the target is no more 1 centimeter cube that you hit with 1 centimeter diameter beam. The target is something like 5 millimeters. The material is a powder, and then you have to do something with your beam. So there is a lot of things to do. This is basically what we have done in the last 6-7 years, trying to use the same machine to do something else, to produce all these isotopes which were not isotopes for which the machine was designed for. The first thing is to buy, and this we went to the market. Whenever we can, we go to the market. We bought a solid target station, which is a machine like this. This is my hand, and this is the target. Basically, it's designed to bombard a 24 millimeter diameter disc with some material which is electroplated on it. But with the powders, this doesn't work. So we have to think something. You will see our solutions. So we developed a strategy. First of all, we want to know very well our beam, and we had to develop big monitoring detectors. So this is translation from high energy physics to medical physics. We had to design and invent another target, and we had also to transfer the target from outside, inside the bunker and out, without entering, because since we have a daily routine production, radiation protection, I'm the radiation protection officer, this is not allowed. I cannot send students putting the coin as you saw with my hand there. It's not possible. So we had to do all that. We had to know the cross-section, because for most of those reactions, they were unknown. And then we had to focus the beam on the spot and possibly modify the beam if needed. This is the active system that we are still developing now. This is the last part of my talk. Okay. Beam monitoring. The most successful one is the unibeam detector, so-called, that became, as you can see here, a commercial product by a Canadian company called DPACE. You can go in the website, and basically is produced by DPACE under our license. And it's very simple. You have an optical fiber doped with typically with cerium, which is this one, that moves left, right, or up, down through a motor and passes through the beam. In this way, we can have a profile. Probably one video is more than 100 words. I can show you live what happened. I just took this video with a handy, with a mobile phone. A student of mine was simply moving the beam with the magnets of the beam line, and you can see the beam goes to the left, to the right, is larger, thinner. So we can adjust the beam live simply by passing through fibers, and this is what the unibeam does. This is the first step. We developed this because we wanted to know our beams much better. We did also our developments, but I have no time today. Then, how can we bombard materials in powders? The first thing to do is to, I just put laser back. We basically compress these powders. This is calcium oxide pellet, for instance. In here we have a pellet. So a small disc, 5 millimeters or 6 millimeters, 500 micron thick. Then we embed it into a coin, because the solid target station accept coins, as you saw, like a Swiss franc. This is basically like a real coin, but we thought to this system kept together by permanent magnets. Important is that this part of material can be tuned in order to tune the entry energy into this point. So we can tune the energy, and knowing the cross-section, we can enhance the production of the isotope we want and reduce strongly the impurities. This is important. How can we bring the target in? We developed this system, very simple, radiation hard. And you can see here the hand of my student. She opens, she puts the coin in, and then just by turning, this system never failed for now. It arrives to the point, and then pluck, it arrives to the station. Then the disk is locked, and it's irradiated, for instance, for half an hour. And then here we have a pneumatic system, so the coin gets here in this shuttle, and then is sent out through this pneumatic path. And we have two deliveries, one in a hot cell where there is the chemistry module, or a second one typically we use to ship this to the Paul Scherrer Institute, the group of Nick van der Meulen with which we have a very strong collaboration. So the chemistry is typically done at the Paul Scherrer Institute, not here. It's 1 hour from there, so we have to organize a transport. Important that this leaves the very high level of radiation bunker and goes out. Where it lands here in the lead pot. And here we did another development. We put a CZT detector here, which is basically a semiconductor detector, very small, to make a non-line spectroscopy like this. In this way, we can directly measure how much we have produced, because we have to know how much we produce of isotopes which are actually non-standard. Important to know, as I told you, since the cross sections are important, we have to know the energy of the twisting beam, which is not trivial. And here we did a project together with CERN, you can see, and by magnetic deflection, we measured the beam energy. And we discovered actually what we already knew or suspected, that the beam energy depends on several operational parameters. For instance, here is the, the angle of the stripping, but also on the magnetic field of the main coil and so on. So we have to keep all this under control to know exactly the impinging energy in our target. We are not bombarding once more liquid. We are bombarding something very small and very thin, and the energy plays a crucial role. To measure the energy in a target station, we cannot not afford to put a big magnet as here. And so we engineered a new kind of coin in which you have many layers, for instance, of titanium and some niobium absorbers. And knowing well the titanium cross-section, which is this reaction, natural titanium PX vanadium 48, to gamma spectroscopy, we can basically through a fit infer the beam energy. This is a new system. We are going to publish this. It was a master thesis of one of my students. And in this way, you can exactly know the energy in the station without using a magnet. Of course, we had to benchmark this system with magnetic device. So this we could do it in the long beam line, which is, as I told you, key for our projects. Cross sections. How do we measure the cross sections? The cross sections we measure through a new system. Since we have powders, the material has not a regular shape. Think to this thing. So this is our target. We irradiate this with a flat beam that we monitor with our unibeam. Typically, we do the other way around. The cross section are measured by a beam, whatever it is, on a very calibrated thin layer, which is known in terms of mass per unit surface. Here you cannot do it because it's a powder. So we invented this, this system to flatten the beam and bring the flatness into the beam and not into the material. It was not easy to convince the first referee, but after that, as you can see, we measured the cross-section of a plethora of radioisotopes for theranostics, scandium, vanadium, copper, several coppers, terbium, and so on, using this station that we engineered and produced. Basically what it is, we have aluminum absorbers on the target. We have the target here, and then we measure the current on target. This acts also like a Faraday cap, so we can repel the electrons. And at the end, we know how much protons hit the target, and on this basis, and on the basis of the activity we produced, measured by gamma spectroscopy, we infer the cross-section of the isotope and also of the impurities. It will take too long to explain you all those measurements, but I took one, which is very actual because this isotope, gallium, is used in clinical practice. So I will tell you one thing. Today, the gallium is typically eluted from a generator, and the availability is very low, very scarce. And producing gallium with a cyclotron, it will be a big advance. That's why we worked a lot, and we published this paper that if you are interested, you can read. And here is the cross-section of gallium-68 from zinc-68 enriched. But pay attention, when you bombard a material, it's never enriched 100%. So you have also other impurities. In particular, this is the nasty impurity, is gallium-67. Gallium-67 comes from two reactions, and we are the first one that we managed to find a system to measure the two, to disentangle the two contributions from the two reactions. But nevertheless, what is important is that if you are with high enrichment, basically you have only the dark reaction, and if you are below 10 MeV or 11, you basically don't have this reaction. So if you want to produce pure gallium-68 for your patient, you have to stay here and to use an enrichment that basically suppress this one. It's not easy to do, but we managed to do this. And now I will give you the results that we had. These are several productions. So these experimental data are in red and in yellow here. Here you see the yield, so the gigabecquerel per microampere hour that you produce, that we calculate through the cross-section. This is the blue line and the green line. And on the right, you have the purity. So we can calculate purity and yield on the basis of the cross-section, and then we can make tests and try. And you can see here that if you stay below 12 MeV, this is 12, you have a yield, which is not the maximum, but not too bad, almost the maximum if you want, but the purity is 99.9%. Pharmacopoeia asks for 99%. So we are very well in line. Here you see if we start going right with the energy, you start having this gallium-67 and your purity drops. Okay, 4 or 5 minutes more. So here is a summary of all the isotopes we produced. Actually, there are several, and as I wrote in the abstract, I concentrate on gallium that we saw and on scandium, in particular on scandium-44. And you can see this line, of which we are very proud of, because it's basically the world record. We managed to produce scandium in large quantity, end of beam 15 gigabecquerel, which is huge. We are still working on scandium-44 to investigate other routes to have a higher purity. And here you see copper. And there are some isotopes which are not medical, in particular vanadium and promethium, that are used for some fundamental physics studies. And I cite here the two publications. In particular, this can be an excellent source for positronium beam, positron beam for producing positronium, actually. And here is the promethium has implication in nucleosynthesis, so it's studied by people involved in astrophysics. So we can do also other kind of studies using a medical cycle. Actually, we do several. Here I don't have time, but we do radiation hardness studies for CERN and for space missions. We also do some environmental physics studies using the neutrons and so on. Let's go back to scandium-44. Actually, we published this paper, and if you are interested, you can read it. That actually this paper, and my group was awarded the IBA Award 2020 for this. And basically what we did together with PSI, with the group of Nick van der Meulen and Christina Müller, listed here. We demonstrated that from a cyclotron, we can produce enough scandium-44. We are able to purify it, to label molecules, and to have good images in mice. So basically, we demonstrated the full chain works. Now, what comes next? To produce these things, it's important not to focus only on the beamline that we have, because basically only us and a few other labs in the world have a beamline, a long beamline in other boundaries. It's expensive and rare. So we try to reproduce something on the research side, which is basically 1 meter. And this is installed in one of our outports. You can see here the cyclotron. We developed together with the company DPACE this small beamline. It's called mini PET beamline, which focuses the beam on the target, which is here. And we put a diagnostic in front of it. For the moment, this is a unibeam. It's not the commercial version, it's our version, but we are thinking now to improve this. And what happens is that if you send the beam and you see that the beam is not perfectly centered on the target, you can automatically change its position and shape through this system, which is the automatic focusing system, which is reported in this paper here. What does it do? Let's suppose this was tested at the end of the long beam line. Let's suppose that you have a beam, which is the red here, horizontal and vertical profiles measured with a unibeam. Okay, this is a good beam. Then something happens. You have a perturbation that actually we produce artificially with our long beam line, and you go to the blue. And this beam is not good because it's, you know, it's 2 millimeters out of the target and basically will produce a very low yield. It's not good for your production because your target is about 5 millimeters, so it's from here to there. The system sees this and brings back automatically the beam in position to the black. So this is proven in the long beam line. Now we are working on this compact system to make it better, and possibly for high current. So we are thinking to a new detector. Okay, time is basically over, and I would like to conclude. I hope I could give you a good example to say that medical cyclotrons can be tools for medicine, for routine PET production, but also for research. And the two things, it's not always so easy, but can run in parallel, and we are a good example. At our laboratory, we do many things, not only routine by the company, but multidisciplinary research encompassing several things: particle detectors, radiation hardness, and in particular, new isotope for theranostics, and we studied quite a lot, and we are continuing. We are open to collaborations, and I'm proud to say that we had also a student from Turkey in the past, from Ankara, that made actually a thesis on the production of scandium from titanium 4 years ago. And we are open for collaborations. Of course, I gave this talk on behalf mostly of my group. It's not a one-man show, and I would like to thank all these people that in the time contributed to these developments, and in particular the lab, our laboratory mechanics and electronic workshop, and last but not least, the Swiss National Science Foundation, which is our funding agency. Thank you very much, and I'm open for questions.
Thanks a lot, Savario, for the very nice overview of what you are doing at University of Bern. We would like you to upload your presentation to Indico if it is possible.
Absolutely.
Sorry, say it again.
Absolutely, yes, sure.
Yeah, thanks a lot. And do we have any questions from audience or Zoom? Yes, Professor Unna.
Thank you for this great presentation. I don't have a question, but a comment. Yep. Ankara, Turkey, there is also such a cyclotron at 30 MeV, which also has a beam line for experimentation, and they are also producing some radioisotopes. I know that on the experimental line, they are trying to do some studies. Since you wrote as your last bullet, you are open for collaborations. I'm planning to send around an email to both parties. Maybe I can be the catalyst to initiate such a collaboration.
Yeah.
Thank you.
Actually, the collaboration that we had already with Ankara was with the METU, our university, and we had this common student, and okay, it worked well once. Of course, we are very open. And yes, I know that there was this 30 MeV, but we never came closer than that. But of course, we would be happy. Thank you for doing that. Very much appreciated.
That 30 MeV machine now is under the supervision of some close colleagues, and they also made a presentation yesterday saying that they wanted to collaborate with everybody. So you both in the same Congress said the same thing, open for collaboration.
Okay.
Unfortunately, not after the other, but anyway.
Unfortunately, yesterday I had exams, as Gohan knows. Can I access the presentation of yesterday from the Indigo? I think so.
I'll make sure that the slides are uploaded if they are already not.
Okay. Okay. For my slides, I will just try to do it. In case it doesn't work, I will send the PDF to you, Gohan, and you can upload.
Sure.
I will try right now. Huh?
Yeah, I just noticed that the slides are uploaded. This is the PHT status and plans at 3 o'clock. You will see.
Okay, I will see. I will see.
Of yesterday, yes.
Absolutely.
Okay, great. Thank you.
Thank you.
So, any more questions? Any more questions or comments? So, otherwise, we thank Saverio again.
Back to you, and I hope next time to be there in person and also be able to see your very nice country, in which I was already once.
So we are looking forward to it, Saverio.
Absolutely. Thank you very much to you and for the invitation. Okay, so we close here. Eh? Bye-bye.
Bye-bye. So we are closing today's session. So thanks a lot for giving the lectures and coming and participating. See you tomorrow.